Okay, let's start. It'll just take, I think, 15-20 minutes. We'll be done with the topic. Okay, so this is the last part of the report. I'll try to solve some recent questions from this chapter so that you get an idea of the key expect korte paro. Chapter is very basic. Okay, there's just 3 equations out there. So before I start, can you give me a reminder of the equations that we learned in astrophysics so far, space physics? I'll help you with the first one. Yeah, so what's the Wien's displacement law? Sorry, what was it? Q2? Inversely proportional to wavelength. No, that will shoot all over. Lambda max. The wavelength of the most intense. Lambda max is the wavelength of the most intense. Right. Okay, yeah, you're right. So, lambda max maximum intensity wavelength. Maximum intensity lambda. Okay, that's the first equation. What's the second equation we learned? It's the brightness of the power of a star. What is that? Power of a star? No. What was it? Into sigma. Okay, so yeah, it's luminosity. So luminosity hoche the power of a star. Luminosity formula hoche L equals to, yes, 4 pi r square sigma t to the power 4. Okay, that's it. So yeah, these are the 2 equations we saw. Chara kichu so far koi nahi amra. Aske hoche we'll wrap everything up. Ja baki ache ekhane ei dutai tomader actually topic. Right. Okay. It's a very important question, actually. So what's the difference between intensity versus luminosity? So let me show you. So intensity versus luminosity. Right. So main difference is intensity as a unit of what? Candela, are you from 2011? Watt per meter square. Candela to 2011 or science right, intensity is watt per meter square and luminosity is just watts. Okay, so this is the main idea. If you can remember this, right, it actually helps, because if you look at both of them, luminosity has a unit that's just watts, right? What else has units of just watts? Power. So luminosity basically means the power of a star at the location of the star. Intensity is watt per meter square. What does that mean? How much power you're getting over area, right? So this is actually how much power you're receiving. So let's say we have a star out there, and the star has a couple of properties here. So let me show you Kioche. So this is a very far away star, and the first property is the power that the star is giving out. Just 1 into 10 to the power 24 watts. That's the power of the star, right? And we are out here very far on Earth. The light from the star is traveling across the galaxy, and the light comes and reaches to you. And as it reaches to you, you have like a telescope or a sensor or something. The intensity you find is 2 into 10 to the power minus 14 watt per meter square. So question is, what is this and what is that? So what do you think is this? This value, this is the power, right? So what would that be? Is it intensity or is it luminosity? Luminosity, right? So this number that you see here, that's the luminosity of a star. It is the power that a star is given to you. And this number that you receive on Earth, is it the actual power of the star, or is it the power that you receive? You receive, right? So what do we call this? Intensity. So intensity is actually what comes to you after traveling all that distance out there. And there's a link between these two, which is a very important link. What's the equation that links luminosity and intensity? বলো। No, no. So this distance is d. This is how far you are, right? And the star was supposed to give you 1 into 10 to the power 24 watts, but you're not receiving that, right? Why are you not receiving that? It's very far away. So we need to find out how your power changes over distance travel, right? And that relationship is the radiation flux from your AS, which is intensity that you receive is equal to power divided by 4 pi d square. Okay, and if আমরা power না use করে, we'll use the luminosity. Okay, so আজকে start করি Hubbles law. Very basic একটা topic, and এটা নিয়ে বেশি question আসতে পারেও না because it's very straightforward. So we have to go back to the origin a little bit. Mock is on 12th. No, তোমাদের যেহেতু ক্লাস ইভেন্টসে নিব, তোমাদের স্যাটারডেতে নিব. Okay. Sorry? No. Astrophysics I'll take later on because I want to do some questions. Yeah, there. I mean, just to check for the I'm বলছিলাম Wednesday, right? 12th February, 3:30. Yeah, it'll be on Saturday rather. Okay, look at this. So you have stars out here and galaxies, and a couple of things I'll be asking. So that can answer করতে পারো নাকি? Let's say you have these faraway galaxies out there. Can you tell me how can you find their distance? Who wants to answer this? It's a 4-mark question. How to find distances of faraway galaxies? So these are all random galaxies out in space, right? How do you find their distance for 4 marks? Who wants to answer? No, it doesn't. Use standard candle method. So who can use the standard candle method and tell me what is the distance of the star or the galaxy from us? Almost there, but you flipped over the quantities. We don't know. Our telescopes can't measure luminosity. Right, exactly. So anyone else wants to give it a try? Like, how can we use standard candle to find the distance of a very far away galaxy? It is the most elaborate question you can get in your exam. Intensity of a standard candle. Or intensity. Achha, okay. Right, so both. But what do you know the luminosity of? The sun, our sun. Our sun is only one sun in the entire universe. So where will I find it again? But it's not a standard, our sun. Supernova. Safe it very well. Okay. Yeah. Right. So, like, step by step. So when you look at very far away galaxies, right? We need to find something in the galaxy whose what do we know? It luminosity, right? Power that we know. So luminosity হচ্ছে বের করতে হবে. Now these are galaxies with lots of stars in them, right? And yes, there could be a star in one of these galaxies that's just like our sun, but we wouldn't know that because it's a blur to us. আমরা individually star দেখতে পারি না এখানে, right? So what do we look for to take place in one of these galaxies? Yeah, supernova. আচ্ছা, specific variable তোমাদের মনে হয় allow করে না. So far Mars মে যে supernova বলছে. হ্যাঁ, but You don't like supernovas. You have been saying about that star from the beginning. Okay, anyways. So, yeah, you have like a supernova that takes place in one of these galaxies out there. And if you look at a supernova, there's an advantage, okay? Almost all supernovas that are out there, we know they're what? Oh no, yes, yes, yeah. So we when we look at them, we know their luminosity, right? But as the light travels all that distance, right, through space, this light is coming from very far away in space, and it comes and reaches our Earth here, let's say. We can use our telescopes to measure the watt of that particular intensity, right? So economic intensity পাচ্ছি. Yes. Yeah, similar. So we have luminosity and we have intensity. So এটা use from a key বের করতে পারবো distance, right? Which relationship do we use here? Intensity equals to luminosity divided by 4 pi d square. And it use করে we find distances of stars out there. This is called a standard pencil method, okay? And back in the 60s and 70s, we mapped about 100,000 of these, you know, যত galaxy পেলাম আমরা ওগুলোর হচ্ছে distance বের করছি. And as we start to look further into their distances, we found that there is a relationship that's developing here. So let me explain what that is. We found that when you look at these galaxies, they appear different degrees of red. So some of them are very red like that. Some of them are mildly red. Some of them are little like orange, right? They have like a very obvious hue to them, and there is like a color part to it. But this is strange, and the reason why it's strange is because all these galaxies are made up of stars, and stars only have certain colors out there. And it's not possible that your star is entirely made up of what? Red giant. This galaxy that's fully red, right? It's probably fully made up of red giants, right? But that's not the case, because once we measured their wavelength, we found something very strange. We found that, and you know this from your O levels, we found that when you look at a spectrum, there's something called the emission spectrum and absorption spectrum. আমরা যখন হচ্ছে কোনো স্টারে দেখি, আমরা typically হচ্ছে emission spectrumটা পাই না, আমরা absorption spectrumটা পাই. So তোমাদের absorption spectrum করে আসছি, আমরা দেখে আসি একবার. So absorption spectrumটা কিরকম দেখতে হয় কি আমাকে বলতে পারবে একটু? Like what does it look like, the absorption spectrum? Yes, so it shows all the colors except the ones that have been absorbed, right? So this is your absorption spectrum. So absorption spectrum, you'll find that you have all the colors available except for some of them that are what? Absorbed. So so what we do here is we looked at all these stars and galaxies out there, and we found that the color that they're giving off, right, is very similar to that of what? Hydrogen. It's a hydrogen spectrum, by the way. But we found something a little off. We found that these are little shifted. মানে এই black লাইনটা যেটা এখানে থাকার কথা, এটা একটু এদিকে চলে আসছে, এটা একটু এদিকে চলে আসছে. And there's a small amount of shift in all the wavelengths that we saw. And this can't be a coincidence that there's another element out there that has this kind of a spectrum, because there isn't. We have mapped all the elements out there in the periodic table. We know exactly what colors they can release. You know, the quantum physics behind how energy shells work is very solid. There's no reason for it to be like different, right? So it means that this shift can only be attributed to what? Hydrogen's wavelength changing for some reason, and not that it's a new element. Because one of the speculation was that it's a new element, right? It can't be a new element. No, we're looking at one galaxy right now, like this galaxy. বাকি কালার গুলো হচ্ছে মানে কোনটা, যে এটা red-ish, which means that it's supposed to be what color? What colors are galaxies? Yeah, so the galaxies are like a mixture of different colors out there because of different stars in them, right? But when you look at them in the spectrum, right, you find they're all what spectrum? Hydrogen. The question হচ্ছে, we did this last class, target class. So why do stars look different color if they have the same spectrum? No. blue giant হচ্ছে blue color, our sun is white yellow, red giants are red. But if you look at their spectrum of the colors and the wavelengths they release, right, they're all same because they're all coming from a star that has what inside it? Hydrogen, right? Why do some stars appear blue, some stars appear red? Right, but why is the color different? Exactly. So what's happening here is that when a star is very hot, out of all these colors that are coming out, right, which color has more waves coming out of that? The blue one. Hot hole blue hoy, right? Ar jeta hocche holo diametric to cooler, right? Otate sob colors ki ashteche, but which colors are more? Red. That's why you have that difference out there. It's not because their wavelengths are different. It's because within the wavelengths they release, some wavelengths have what? More intensity. And that's why they appear more red, more blue. So otherwise it will be a confusing thing, right? That একটা স্টার দেখা যাচ্ছে red. Now এটা কি red temperature-এর জন্য নাকি red redshift-এর জন্য? ওটা আমাদের confusion হয় না because যেটা temperature-এর জন্য red, it's still given a spectrum that looks like what? This. But ওদের দেখবা যে এই যদি গ্রাফ প্লট করো intensity দেখবা যে intensity এরকম দেখতে। Which parts of the spectrum has more intensity? The red part. So they'll appear more reddish in color. Okay, that's how we know that there's still hydrogen. Okay, so yeah. ওটা দেখবো redshift কি হয়. So yeah, the displacement, Wien's displacement law. So the law states that when you look at colors coming out from an object, the object has a very specific requirement. It has to be a black body radiator. It's an object that has 100% efficiency of releasing energy. If you look at the highest wavelength intensity, মানে অনেক কালার বের হচ্ছে কোন wavelength is the highest intensity light. So let's say you have red, green, blue, সবই বের হচ্ছে, but red the highest intensity. So red এর wavelength তোমার lambda max হবে। বা আরেকটা স্টারে বা অবজেক্টে দেখো ব্লু কালারটা সবচেয়ে হাইয়েস্ট ইন্টেন্সিটি দেয়, তাহলে ওটার ল্যাম্ডা ম্যাক্স ব্লু কালারটা হবে। Once you place that one here, and there's a constant here 2.898 into 10 to the power minus something, then notice korba that the temperature that you get is the surface temperature of the star, and we find that higher the wavelength, shorter the temperature, less the temperature. তার মানে রেড যত বেশি হবে তত কুলার হবে, আর যত ব্লু বেশি হবে তত হটার হবে, and that's the Wien's displacement law. That's how we know the temperature of different stars out there. Okay, so coming back to my point, এদিকে দেখো কি হচ্ছে, let's focus. এটা আজকে শেষ করতে হবে। Yes, দুইটা ওয়েভলেন্থ যদি সেম হয় মানে একটা স্টার থেকে দুইটা কালার হাই ইন্টেন্সিটি হচ্ছে, এটা পসিবল না। There's a distribution graph out there, এই যে here এরকম দেখতে হয়। সো তোমার যেটা হবে পিক চেঞ্জ হয়, এদিকে যায় এদিকে যায় এদিকে যায়, the distribution is always like a bell shape, so it can't be like this. এটা পসিবল না। Okay, so why is this happening? So you have to go back to your AS. So can you remind me from AS, right? There was this thing called a Doppler effect, right? Let's just quickly do that. What's the Doppler effect? The apparent change in what? Observed frequency due to the movement of the source relative to the observer. আমাদের কিন্তু সিলেবাসের মধ্যে we were stationary. What was moving? The source. দুইটাই হয় কিন্তু, but the other one is not part of our syllabus. So what are we? We are stationary and we are observing the what move around. Galaxies move around or objects move around, and we learn in AS that as things move away from you, the wavelength we hear or the frequency we hear, if they move away from us, is a low frequency, high wavelength. And if the object is coming towards us, it's high frequency, short wavelength. So basically, as objects go away from you, this is what you need to remember. As objects go away from you, wavelength increases. As objects come towards you, wavelength decreases. Is the actual wavelength of the source changing, or is it the observed one changing? Observed one. So actually, so if you're in a car and you're listening to the sound in the car, it's the same. It's just somebody else outside the car hears the sound differently. And this is possible for light as well. So if a car goes past you and you see the light, right? Light can color change for a kotha because of red shift and blue shift and everything, Doppler effect, right? But we don't see that happen. I'm not really sound like an ambulance goes by, a car goes by, a plane goes by. It's very easily noticeable. Why don't we see a car's light change color if it's moving past us? Small distance, nah. Yes, so the thing is, the amount of shift that's possible, it's actually proportional to how fast you're moving compared to the wave speed. So our sound speed, what's the speed of sound? 333 meter per second. A car going is 30 meter per second. That's like 10% the speed of sound, right? তার জন্য shift actually 10% হয়। ওটা আমাদের possible বোঝার জন্য। Your car going at 30 meter per second and speed of light is how much? 3 into 10 to the power 8 meter per second, right? How much of a fraction is that? It's like 1 billionth of that fraction. তার জন্য light কিন্তু change হচ্ছে, but 1 billion change কি আমাদের eyes notice করতে পারবে? No, that's why you don't see it. So that's why when light-based objects undergo redshift and blue shift, we normally don't see them on Earth is because they're moving very slowly. But turns out, luckily for us, right, galaxies are moving at very high velocities. Their velocities are 10 to the power 6, 10 to the power 7, 10 to the power 5. So ওরা যদি move করে, wouldn't the color their shift be very observable, or we can notice that? And that's exactly what happens here. When you're looking at galaxies and faraway galaxies, this is the formula we use. Change in lambda. This is right. So change in lambda formula. This is how you find the speed of galaxies out there. Change in lambda by lambda is equal to V by C. Contact here to explain because this is almost guaranteed in your exam. Like actually, last paper so there's a good chance to ask, okay? So asking the formula, and there's a mandatory space physics question. So 80 আসার chance আর কিছু নাই. So this is speed of light, which is 3 into 10 to the power 8 meter per second. This is the speed at which your galaxies are moving. এটাকে usually বলা হয় recession velocity, and the reason why it's called recession velocity is because all the galaxies are moving away from us. ওই process থেকে বলা হয় recession, recede করে, আচ্ছা? And this lambda is where confusion takes place. Let me explain. This lambda is the lambda of hydrogen on Earth. মানে হচ্ছে it's the wavelength of hydrogen, right, without what taking place, any shift. এটা হচ্ছে Earth that we can figure out, right? And a change in lambda টা হচ্ছে lambda observed মানে from our stars and galaxies minus lambda on Earth. So আমি এটা হচ্ছে originalটা দিলাম, E দিলাম, আচ্ছা? So এটা E তোমরা এক্সামে লেখো না, just বুঝানোর জন্য দিচ্ছি, okay? So that's your change in lambda. And turns out this change in lambda that you have here is proportional to how fast your object is going. কেন? এটা একটা constant, এটা একটা constant. এটা কেন constant? That's the speed of light. এটা কেন constant? That's the spectrum of hydrogen. It's the same for hydrogen no matter what you do. তাহলে তোমার যত জোরে গ্যালাক্সি গুলো যাচ্ছে তত বেশি কি নোটিস করবা? Shift. Like the more the shift is, and the more the shift is, the more what will the galaxies appear? Reddish in color, right? Because they're undergoing more redshift out there. And as a consequence, what we notice here is that objects that are a little close to us, they appear orange. Objects that are very far away from us appear red, right? And আমরা plan করছি যে we'll look at the relationship. Why are they more red like that, right? And we found this graph here. So এটা হচ্ছে distance of your galaxies. It is measured in light years, and this is the velocity of your galaxies measured in meter per second or kilometer per second. And we found that this is how the graph looks like. All the galaxies that we have found, they appear to have a relationship that is quite obvious, that it's a linear relationship, directly proportional. And once we plotted the graph, this is basically work done by Edwin Hubble. He found that the velocity at which your galaxies are receding is directly proportional to what? How far they are. So velocity হচ্ছে যে rate ওরা যাচ্ছে, and distance হচ্ছে like the galaxy distance, right? So it means that the further you are, the what you are, the faster you are. This is a very important discovery, by the way, okay? Because there are like other discoveries out there in astrophysics. One of them being the redshift itself. ওইটা বের করার পরে we understood that the universe is expanding. But that's fine. It could be like the things are just moving around randomly through like a medium in space. But this particular observation was more important. Why? We found that they're not just moving away, they're actually accelerating, which makes it very complicated. And the reason why it becomes very complicated that they're accelerating is because from Newton's laws, classical mechanics, right? If there's acceleration happening anywhere in the universe, there must be a what acting on that system? A force, not just a force, a resultant force. And that is where we are stuck right now. We don't know what is the force that's pushing all the galaxies away, because we know galaxies are all accelerating away, right? And there must be a force on them, because simulation যদি run করো তোমরা our universe, right? Like, you put galaxies and try to see what happens, সব collapse করে. They all just collapse back in. Why do they all collapse back in? Because there's one overriding force that's always everywhere. What is it? Gravity. And gravity of all the masses will just bring everything in, right? But contrary to that, it's actually contradicting it. We see everything is moving away. It's like gravity is not bothering you at all. It doesn't even exist in our system, which is strange. And that's why we came up with some ideas out there. A force wrongly named, by the way, it's called dark energy. So we call it dark energy. It's the force responsible for expanding our universe. Its origin is not known. However, its origin can be traced back to equations of Einstein. So there's one speculation out there. This dark energy has been predicted. Einstein's equation has it. So Einstein equation predicts that there's this external repulsive force of gravity, and it only acts at what range is really far away. We still don't know if it's true or not, but the thing is, we at this moment, there's nothing clear about it. We just have speculations of it. All you need to know is that this is a fact. তোমরা কিন্তু জানতে হবে না why. You need to know the what. So what do we know? We know that the universe is expanding, and it's expanding at what rate? Accelerated rate, right? And a accelerated rate as you expand is a name for that universe. It's called a open universe. So there are three types of universe models out there. You have flat universe, open universe, and closed universe. Closed universe could be simple buchte, but fortunately or unfortunately, that's not true. Closed universe, the universe is like a starter moton and explode korlo big bang er jonno, and the universe is expanding and expanding. That's like the radiation pressure. And then what's trying to bring it back in? Gravity. And at a point, the radiation pressure falters, and who takes over? Gravity. And what does the universe do? Collapse back in. It's called the closed universe. It's called a big crunch. And we thought that this is probably what's happening, because gravity always brings everything back in. It keeps happening like that, right? But then few years back, actually, I think 2010, we have proven it mathematically that crunch possible now. And we have further proven that the expansion data hochilo, we had a model where it was expanded, and the expansion reaches equilibrium. Money, it's expanding terminal velocity, but at what rate? Constant rate. Because the gravity and the outward force balance each other out. And if they balance each other out, what happens to the resultant? Zero. So will it stop, or will it continue to move at that same rate? Continue move at that same rate, right? Only the universe just stops. Now, flat universe, no, they think that it just stops at that point. No, it still continues to expand, but at a what rate? A constant rate, right? But that's also proven wrong. So the one that we know right now with evidence and data is that the universe is not only expanding, the expansive force is easily outweighing which one? Gravity. Tarjuna, it's not only expanding, it's accelerating in its expansion. And this is referred as the open universe. And it's just going on and on and on. And we predict that it'll keep going on like that for 100 trillion years, to a point that every single proton in your body would be light years apart. That's what's going to happen eventually. That's called the cold death of the universe. Like stars like in the context of the universe, stars and galaxies will disappear very soon. The burning process will stop. The universe will be littered with what only? The remnants of a dead star. The white dwarf turn into a black dwarf. Just Ogla float kore berache. Ogla will be ripped apart at one point, and every single proton that you see will become what? Far away from each other. And that's where something very interesting shows up. Protons actually have a half-life. Contrary to what we think, protons are not stable. They actually can decay, but their half-lives are 100 trillion years. So তখন আস্তে আস্তে প্রোটনগুলো কি করা স্টার্ট করবে? Decay করা স্টার্ট করবে, and every proton in the universe will just disappear. And at that point, it'll be just littered with random subatomic particles out there, like mesons and muons. Remember leptons from your AS Ogla, and that's called a cold death. The universe will reach what Kelvin? Zero. Do you get my point? That's the end of the universe. Now ওইটার দিকে যাচ্ছি আমরা. So যে তোমাদেরকে analogy দিলাম না, you open a Coke bottle. So you're right now at the open করার পরের first few seconds. Imagine you wait for 100,000 years with the Coke bottle. What would you see happen? Just everything will just disappear, right? That's what's going to happen. Like the bubbles to dure kotha. Are you expecting a bubble to be there 100,000 years later? No, right? Coke tai to thakbe na. So that's what's exactly happening. The energy that we have, the energy you see, the sparkle and the twinkle of the stars, will shall disappear within the next 100 billion years, because stars will start to die out. they will not reform anymore. Bolo? What's been conserved? What's that energy? Dark energy, the force. Yeah, they called it the wrong term. They should have called it dark force, but apparently it was copyrighted by Star Wars, so they can't do anything about it. so yeah, they had to go for dark energy. Correct, right? The protons in your body will be ripped apart and they'll be light years apart. Yeah, but the thing is, the rate of expansion is so strong that going back and fusing together, it can't take place anymore. The fabric of space would be that far apart. Like every point, black holes will evaporate. So there's the thing that once a black hole forms, right, it consumes masses and grows. But if it doesn't get enough mass, it'll start to shrink and disappear. There's nothing to sustain. Oh, so those masses actually released by the black hole, by the sides of it. It's called the Hawking radiation. There's a speculative white hole as well, which is supposed to be the place where all the mass is coming out. This black hole doesn't defy laws of physics, like mass conservation, energy conservation, information conservation. These all do take place in a black hole. It's just that it's not like the way we think it is. Like this mass going in and it's just gone forever. It's not like that. It's actually given out as radiation later on. Achha, so this is called the Hubble's law. Now to clarify a couple of things before we end this. So as you can see, it's a straight line, and straight line thakle hocche physicists try to find what from those graph gradient, and they found the gradient of this graph here, and that would make my equation like a equal to equation with a constant, and the constant was H naught D. IGCSE students should know this. This H naught is called the what? Hubble's constant, and etar value hocche jai ami bolbo is wrong. Acha, mane tomar boito deoar wrong, online or wrong, sob theke wrong. I'll tell you in a minute why. So Hubble's constant hocche 2 into 10 to the power minus 18 as per your syllabus. But yeah, the value in the front is it goes from 0.5 to 5. Mane 10 times vary korte pare, but the minus 18 is important. Now here's the question: a Hubble's constant ki signify kore? It signifies the rate or this gradient here. So এটা use করে আমরা কি করতে পারি? So now comes this part that earlier some of you asked me. How do we find distances of all galaxies now? So আমরা standard candle কেউ use করি না. We don't use annual parallax, or we don't use any other method out there. We just use this graph here. What I need to do is I need to look at a galaxy and find the what in that galaxy, the redshift. Once I know the redshift for that galaxy, what can I find for that galaxy? The velocity. And once I know the velocity of that galaxy, I can just put it into the graph and find its corresponding what? Distance. And that's how we now find distance of all galaxies. So galaxy distance বের করা এখন হচ্ছে backyard astronomers are not possible. You just need to have a telescope that can pick up redshift. And once you have the redshift, just plug it into this equation. The only source of error in the equation is which one? The Hubble's constant, because oita hocche একটু controversial. I'll tell you why it's controversial. The Hubble's constant can be used to find the age of the universe. And এটা তোমাদের O levels ছিল, A levels নাই. Age of the universe হচ্ছে formula হচ্ছে age of universe মানে estimate যদি করতে চাও is equal to 1 divided by what? Hubble's constant. And এই যদি 2 use করো 10 to the power 18, তাহলে it comes around approximately 13.6 billion years. That's the commonly accepted one. However, Hubble's constant কিন্তু fluctuate করে, as I told you. So 0.5 নিলে দেখবা এটা আরেকটা নাম্বার আসছে মানে আরো বেশি. It's like 15 billion years old, 16 billion years old, some estimate 11 billion years old. So Hubble's constant actually is dependent on how old the universe is. Since we don't have that information, the constant হচ্ছে vastly vary করে. Also, it's not really a constant because in the future, a graph actually কি করা start করবে? Shift করা start করবে. কেন shift করা start করবে? এর gradient আস্তে আস্তে flat হয়ে যাবে. কেন gradient flat হয়ে যাবে? Gradient যদি কমে যায়, তাহলে যে Hubble's constantটা যদি কমে যায়, তাহলে age of the universe বাড়তেছে না, and age of the universe তো বাড়বে. It's not going to be stuck at 13.6 billion years for the rest of its time, right? As time goes by, এটা বাড়বে না. So let's say 20 billion years later, some physicist looks into the Hubble's constant. Same থাকবে না তো, but 20 billion years এর জন্য যে ভ্যালুটা আসবে সেটা আসবে. So do you understand why this is not really a constant? But from our point of view, for the next, let's say, 100 million years, it doesn't change much. Is such a small amount, 100 million years, in the context of 10 billion years, right? So right now, we're glad that we have some number. Because prior to this, like, some of the greatest physicists thought the universe was eternal. There was no beginning, there's no end. But now suddenly we have a beginning. And because now we have a beginning, we have more problems. Problem number one, how did it begin? Right? So that's the bigger problem. So here, physicists, really astrophysicists, they had a very nice time. Another life just start dekha and finding distances and maybe figuring out data ki galaxy na ki star. Ite oder kaaj chilo at the point. Now they have to figure out how did the universe form, right? So that's what they're doing right now. So, and they're not doing a good job of it. So the thing is, what is the current theory out there? So current theory এখান থেকে আসে, theoryটা হচ্ছে, and we have done this before, so তোমাদের 4-mark একটা question আসতে পারে. Explain how the cosmic redshift gives evidence of the Big Bang theory. So first of all, let's try to understand what's the Big Bang theory. So the Big Bang theory states that the universe was there all the time. It's not the one that you probably heard something happened and the universe formed, or the universe was already there. What size was it? It was very small, very dense, very hot, and the matter was all clumped together. What matter? We are still not sure, but we understand যে muons, leptons, gluons, এই জিনিসগুলোর একটা soup ছিল. Like they're just mixed around, going from this to that. It was very small. Physics was very different there. ওই structure ভিতরে, not the physics we know. And then something happened. Like we don't know what it is, but it triggered the expansion of it, and it started to expand. That expansion event is called a Big Bang. So Big Bang কিন্তু not the start of the universe, it's the start of the what of the universe? Expansion. Okay, তার আগে universe ছিল, and now we're just seeing the expansion taking place. So the question is, why is it not possible that we see a telescope and look far back into time? You understand, right? When you see it using a telescope, you can see much further back in time. Why is it like that? Because objects that are, let's say, 15 billion light years away, hypothetically saying, right? ওইখান থেকে light আসতে কত time লাগবে? Right. So universe যদি 13.6 billion years আগে form হয়, aren't you not in theory seen before the start of the universe? Right? That's supposed to be the case, right? And that's actually true. And that's why we build like a $4 billion telescope and we send into space, the James Webb Space Telescope. ওইটা এখন কি চেষ্টা করতেছে? To find the oldest light in the universe. That's its main purpose. If you find the oldest light in the universe, you can see the beginning of the universe, right? And ওটা করতে গিয়ে, I think I told you, things got bad. Now the oldest light of the universe, আমরা speculate করতাম, will come from maybe a star that just born, or maybe a galaxy that might try to form. But mostly we thought we'll see nebula. That's what we were expecting, because that's where stars came from, right? But just 100 million years after the Big Bang, our theory te ja bole, nothing should exist, right? Because it's just 100 million years. Star formation to porer kotha. We are seeing full galaxies right now. That's the problem. Okay, and we don't know what the solution is. So a paper release of it very soon, but because 1 year where you said they have peer reviewed it, that some of the oldest galaxies we have found, right, they're so mature that their existence should take 2-3 billion years old, and we're seeing them right at the start of the universe. So there's only one of two solutions out there. One is that the obvious one, that we have made a wrong estimation for what the age of our universe, because the time is wrong. Arta hote pare, which is the more speculative one, right, is that galaxies were already there before our universe formed. These are not galaxies of our universe. Yeah, so there are other universes around. So now there's like a lot of theories out there যেটা অনেক হচ্ছে throw around করা হতো of multi universes, and আমরা ভাবতাম multi universes মানে হচ্ছে আরেকটা universe where you have like a better understanding of physics, right? But it's not actually like that. Multi universe is basically an entirely different universe out there with different physics, right? ওগুলা exist করতো in theory. Math কিন্তু very convincing evidence আছে. Now maybe we are actually getting experimental evidences that they exist out there. Some of them probably can create what? Galaxies. Some of them can create matter that are going through us right now. We can't feel them, but it's all around us. And one of such matter is what? Dark matter. Dark matter is 86% of our universe. It's like 86% of the universe. I'm not going to idea. Because that's what dark matter is there. It's everywhere, right? So it's what keeping the universe together. We have zero clue about it. The only clue we have is what? It has gravity. That's it. Ar kichu jani na. So we have tried detecting it to no avail, right? But we can see its influence everywhere in the universe. So now speculation is dark matter could be influence of what? another universe onto our universe, which is like intertwined with our universe. Maybe different dimensions. That's why we can't see anything from there, but we can feel what from there, the gravitational field. Possible. I said these are all speculation. So coming back to our Big Bang theory, so how does this redshift confirm the Big Bang theory? So redshift is telling that things are moving away faster and faster. So I'm at the analogy day, last sector finish before we end. Let's say you drop a ball and ball is falling due to gravity. And ball speed and it's getting faster and faster, right? Now if I start to rewind this video, like of a ball falling, right? Wouldn't the ball start to go back and back and back and back and back slowly? So we basically did that. We saw the rate of expansion of the galaxies, right? And we started to rewind that. A rate, if I start going back, how back can I go until my velocity becomes what? 0. And that's when we found 13.6 billion years as well. Mane graph chara, that's why the Big Bang theory is very commonly acceptable like a theory, because we have many evidences for that. Okay. There's something else though, syllabus and cosmic microwave background radiation. That's also something that was released during the Big Bang. It's everywhere in the universe right now, and it does match the value here as well. So yeah, at this moment, we are at a crossroad. Things can go different places. We don't know exactly key, but in the next 10 years, the books that you're seeing right now, they will be obsolete. At least the astrophysics part. Star formation, galaxy formation change, but the cosmology part, like the overall picture of the universe, is going to change, definitely. Okay, so yeah, that's the end of your topic. There's this one answer out there. Explain how redshift gives evidence of the Big Bang theory. Just the formula V equals to HT. Right, so you can ask me your questions. So we don't look at the overall color for redshift. We look for what? Individual wavelengths. So that's why you don't need to really bother whether it's overall blue or red. You just see individual wavelengths and they will be shifted. Well, intensity ke ignore kori amra. Bolo, our question thakle. Just this thing here. These 3 things. Yes, I can tell you everybody possible now there, based on what the syllabus says. Are we back to the equation? Luminosity or Wien's displacement law? Cosmology, just say 2. Okay, so let's read through this. So what's the redshift? When distant galaxies are observed, it is found that the spectrum obtained from these galaxies produce a spectrum which is slightly what? Redshifted. The shift in frequency can be attributed to what effect? The Doppler effect. And this shows that galaxies are moving away from us. That's the first thing, that things are moving away from us. Hubble's law ki bole? When it was then found that the further the galaxies were, the faster they're moving. This meant the universe was not only expanding, but rather what? It is accelerating in its expansion, which is important. This is known as the Hubble's law, and it can be related to the equation V equals to HT, which tells you the further the things are, the faster they are. And that is also a property of things that are undergoing what? Further they are, faster they are. Acceleration. So mone hoche V square equals to U square plus 2s. So jodi amar hoche further they are, faster they are, acceleration must be there, right? And lastly, the Big Bang theory. The theory suggests that the universe was dense, small in size at the beginning. It then started to expand, and what the data from the galaxy suggests is us that the expansion is still going, so it's still happening. There's actually information out there that the expansion is right now so fast, right? It's expanding faster than the speed of what? Light. So at the point, because the light before the light can reach us, it's going further and further away from us. Now, students then have a confusion that we know for sure mass can't travel faster than the speed of light. Mass can't travel at the speed of light. So how can it go faster than the speed of light? So you have to be careful here. What's expanding here? Are galaxies expanding, or the fabric and space they're in? Space or mass? Nothing. There's no mass. At negative. Negative actually now, but it doesn't have any mass. It's just like space. It's a vacuum of space, right? So it can travel at whatever rate it wants. There's no problem with that. Okay, so OE expansion will be part. Okay. Photon lose energy. Why? Right. The frequency decreases. No. E equals to hc by lambda. Wavelength is increasing, energy is decreasing. Yeah, so decrease happens, but this is an apparent shift. This is actually a wave property that's happening. So not a particle property out here. So what you're receiving are not photons. What are you receiving? Waves. So if you want to use that wave and do like photoelectric effect, then the energy will be less because now it's a reddish color light. Okay. We can use the just to predict the universe's past in the past was smaller in size. This process of expansion from a small volume and high density is referred as the Big Bang theory. Now, একটা theory exists, which we use actually indirectly. So there's a particle called the Higgs boson particle. অনেকগুলো particle like the quarks and the leptons, right? So there's this particle called the Higgs boson. It's very famous in physics because it's a particle that's supposed to provide us what? Mass. The concept of mass comes from the Higgs boson. It's in every one of us, right? Turns out the conditions necessary for Higgs boson to be generated is only possible if our universe was the size of a watermelon. So now we understand that with Big Bang theory, there was actually a point where the universe was what size? A watermelon size. ওই watermelon size যে density, temperature can only like create what particles? The Higgs boson. So that's where the Higgs boson came from, and that's where the mass in the universe came from, which is very small in amount, by the way. If you look at the bigger picture of our universe, right? What do you think is the percentage of mass in the universe? The universe size, how much percentage of the entire universe has mass in it? 20%. It's 1 by 10, so basically 10 to the power minus 18%. So negligible. So it's barely anything. If this room was a universe, right? And every atom of gas particle here was like, a galaxy, right? It'll be a much more dense universe than our universe, where, by the way, gases are very, far apart. My point I'm trying to say here is that universe mass is only calm. On top of that, there's another anomaly you learn, probably you've heard about it. Mass অনেক, but কোনটা খুব কম? Antimatter. So matter and antimatter can be equal amount to produce at the start of the universe. That's what we believe, right? But all the antimatter disappeared. Only what got left behind? Matter. Now, the way we know matter can disappear is how? Antimatter and matter যদি collide from the last chapter, what do they undergo? Right. So that's the only way we know, right? So where did the antimatter go? So a discrepancy is also not well understood. We have a lot of theory out there. One of them is that it transferred to another universe. Antimatter এখানে ভালো survive করতে পারে. That universe is an anti-universe where antimatter domains like dominates there. Probably oikanka physicists are wondering where the matter went. Could be. We don't know that, right? Achha, so I'll show you some animations here before. Oh, they reverse it. So what they do is first they find the redshift, and there's a redshift out there. So you know the amount of redshift. You dial it back to its normal amount, and then you look for the intensities because we need the highest intensity. Wavelength is not important for us. We need the highest intensity, but redshifted highest intensity will be different, right? So we have to first revert it back to its original value, then we look into it. Acha, show it to screen. Let's see some of the things I've discussed. So এটা তো তোমাদের দেখাইছিলাম, but এটা আরেকবার দেখাই. This is how like different stars color changes. So do you see the left color? Check করে দেখো, we are still producing fairly which spectrum? The entire spectrum. I mean, there's a lot of all the waves almost available out there, right? But if I go to the left, which part is the highest part? Red. It appears reddish in color. So red is the most dominant color there. But as I start to go here, it's a bit like green, blue. So it's like a mixture. And if I go further this way, it starts to become more and more blue. And a point you can't really see much. And at a point, we speculate that you won't be able to see it at all because it starts to emit what radiation? Ultraviolet. So in theory, there's no star like that yet. But there's a possibility there might be a star that's main dominant color is which color? Ultraviolet, because it's so high in temperature. তোমার ম্যাথ করে দেখতে পারো ultraviolet wavelength দাও lambda max এর মধ্যে temperature পাবা, temperature কিন্তু অত বেশি না. So there is possibility that there are stars out there that are ultraviolet stars. Okay. And so there's no way we can say. So there's this speculation. Infrared now we know because of your James Webb, because it's actually infrared color telescope, right? Now look at this. Galaxy Earth move start which kind of wave are you observing? What shift? Blue shift. The Earth is so blue color. On the other side is what? Red, right? But if the galaxy starts to go the other way, you start to notice from the other side. Yeah, that's what we're seeing right now. So that's the evidence that the universe is what? Expanding, because it's all moving away from us. Do we see any stars or galaxies that are blue shifting? So blue shift ki dekha jay. So blue shift dekha jay for some stars in our Milky Way, but not any galaxy out there, because every galaxy is actually moving away from each other. It only boosts the problem. I'll show you an animation for this. This is yeah, it's a very interesting animation. So right now this is the Earth here, and tomoder jeta korte hobe, this is what would have been observed if the universe was what? Static. Do you see that same wave ashtase sob jagah theke color change hocche na, right? So we are assuming that our galaxies are given out a wavelength of how much? 500 nanometer. But when we actually observe, this is what we find. So do you see that there are variations in your shift? Acta red, acta yellow, acta orange, acta green. Do you understand why there's a variation in the shift? Because they're all moving at what rates? Different rates. Which one will undergo the greatest shift? The very far out one out there. Animation's main purpose is to explain to you that at one point we'll never see stars anymore and galaxies. The outer galaxies will disappear. Can outer galaxy disappear? It has redshifted so much that the light it's given out right now is what light? Infrared. And at the point it'll start giving out what? Microwaves and radio waves. Can you see them? No, right? So speculation is like, 100 million years later, like night will appear much like night sky. It'll be much darker. There's majority of the galaxies will have undergone such a shift that they're no more producing visible light for us. Okay, and 2-3 billion years for it'll be complete darkness. You wouldn't be able to see them anymore. Okay, because they have shifted so much that they're gone beyond the spectrum. So maybe radio telescope dekha jete pare, but not visibly. Okay. Yeah, but not like collide. They phase into one another. Oh, it's like our Milky Way, by the way, has 3 small galaxies going around it. Because our Milky Way has a very strong gravitational core, right? There are dwarf galaxies around us. Our Andromeda is also with some small galaxies around them. Milky Way and Andromeda are actually going around in a binary system. They have a common center out there. But over time, what's happening is that they're like moving towards each other. So I don't know the exact time, but within some years, right? The Andromeda and the Milky Way, they'll actually collide. But they can't really collide because galaxies are about 90% empty. So it's just phase through each other. Yeah, merge away, a new formation of it. Some stars will collide, some black holes will merge, but majority of them will just go past each other. Okay. Yes. Further, and in our math we assume we are stationary at the center, but everything is moving away from each other. So the actual redshift of those galaxies could be even higher.